Hi students, welcome you all for control system lectures. In the previous class, I have given introduction to Nyquist plot and we discussed the different stability conditions that are required to set the system to be stable or unstable based on the Nyquist plot. As we discussed in Nyquist plot, initially we will be drawing a Nyquist contour in S-plane. The contour will be surrounding the right half of S-plane. The whole right half of S-plane will be covered in the contour except the origin, pole set origin and the pole set imaginary axis. So except that we'll be covering whole right half plane. Based on that contour, we'll be mapping the locus in G of S plane. So here we'll be having two planes. One is S plane that we can draw based on the transfer function, given transfer function, and we'll be mapping that contour. That contour is called as Nyquist contour, which we are writing in S plane, and that will be mapped to G of S plane. So that G of S plane locus is called Nyquist plot. So we'll start uh, solving this problem. So if you observe this transfer function, this is having a pole at origin. This is type 1 system. So other poles are on left half of S plane. So there is a pole on origin. So therefore we have to eliminate that particular pole while drawing the contour, Nyquist contour in S plane. So first step is once we consider this first equation 1, we have to convert this particular transfer function into a constant form, that is a time constant form. Okay, so let us consider and draw. If you see, we have s plus 2 and s plus 1. What we need to do is we have to write in terms of tau s plus 1, in terms of tau s plus 1. Therefore we have to take 2 and 10 as a common from the denominator. So if you take that common, what happens to the transfer function? G of s is equal to k by s into 2 common, and what it becomes is s by 2 plus 1 and 10 common from this point into 10 s by 10 plus 1. Right, so this is how the transfer function will converts, and once we take out this 10, 2 and 10, what we need to do is we will be sending that part into numerator. So how it becomes 0.05 k divided by s into 0.5 s plus 1 into 0.1 s plus 1. Right, so let us consider this as equation 2. So as I mentioned, we have to write contour in the s plane. How to write the contour in the s plane? So if you see this, there is a pole at origin. So what we can do is just draw a contour which covers whole s plane. So there is a pole at origin. This should be eliminated, and we have to cover whole s plane. Therefore the contour will start from here, it will go till here, and it will come to this point, and here it will end, and it will cover this point. It is a circular contour going in the clockwise direction. Okay, so this is j omega, and this is called s plane. So direction will be on clockwise, this way, and this one. So here this whole contour will be dividing into 4 parts. As I mentioned in the previous class, if you observe, the same plot we have drawn and explained how can we divide that contour into different parts. Okay, here let us consider from this point. This point is 0 plus. Okay, it's actually about the origin, near to the origin. Since we have to represent it, I am writing little bit away from the pole. Actually, this is the origin point. Okay, origin in the sense the pole, eliminating except the pole, the leftover point. After the pole, whatever the point is there, that particular point. So that we can take it as 0 plus. Okay, omega is equal to 0 plus frequency from that point to the frequency till omega is equal to, sorry, infinity. Frequency till infinity plus. And from this point it will be going towards a whole right half plane. This is like r tends to infinity. Okay, I just explained about this plane in the yesterday's class, previous class. If you want a clearance about that, you can just go through that video once again. So this is r tends to infinity. This is radius till infinity. Okay, so it is covering whole right half plane. So this is this whole plot or locus can be considered as a C2. So this is C1 from here to here. From this point to this point is C1. From end of the C1 to till this point, this is C2. Okay. Then from here it is actually minus infinity. Omega equal to minus infinity. Right, omega is equal to minus infinity, sorry, infinity minus actually, that is till infinity minus, and this point we can take it as C3, right, this locus from minus infinity minus to omega 0 minus. Okay, then this particular thing which is encircling or semicircling this pole is considered as C4. Okay, so these are the 4 points. This is at this point r will be 0, radius will be 0 at pole, right, origin. So this is called Nyquist contour. Nyquist contour. So what we need to do is we need to map all the points starting from C1 till C4, C1, C2, C3 and C4. We have to map this in g of j omega axis or g of s axis. So here the transfer function which was given is g of s into h of s. Okay, g of s into h of s. I just not mentioned h of s here. You can take it as g of s itself, or anyway we have mentioned in the problem. So I will just right, consider this as g of s into h of s. Okay, so mapping of each point to be performed starting from C1 to C4 separately, like individually we have to do it. C1 once and C2, then C3 and C4, right, to obtain individual sections actually, right. So in the first case what we can take is C1. Okay, let us consider C1 in S-plane and map it in G of S into H of S plane. Okay, case 1, that is mapping of section C1. Okay, so from here, from this point at omega equal to 0 plus to omega equal to infinity plus. So this particular thing we have to map it in g of j omega and h of j omega axis. Simply I'll call it as W plane. Okay, so omega will be varying here. If you observe, omega will be varying from 0 to, sorry, omega will be varying from 0 plus to infinity plus. Okay, so the locus is nothing but the polar plot of g of s into h of s. So if you remember the polar plot, the first step what we consider is taking s equal to j omega. So consider s equal to j omega, substitute s equal to j omega in equation 2. Right, this is the equation 2. Just substitute s equal to j omega. What we get is g of j omega into h of j omega, that is equal to 0.05 k divided by j omega into uh, zero point 0.5 j omega plus 1 into 0.1 j omega plus 1, right? This is how it will come. So from here what we need to do is we will take j omega as common from denominator. Okay, see here what we need to do is we need to segregate real and imaginary parts. Okay, so once we take j omega common and solve for real and imaginary expressions from that plot, how it becomes is 0.05 k divided by real part will be 0.6 omega square plus j omega into 1 minus 0.05 omega square. So when the locus of g of j omega and h of j omega crosses the real point, the imaginary term will be 0. So this we discussed while explaining the polar plot, the first method. So in polar plot we discussed the two methods. In first method what we were doing is to select if the locus is starting in the imaginary axis and intersecting the real axis, what we need to do is imaginary part should be taken to 0. Corresponding frequency and corresponding frequency at which that it will intersect that real axis. Okay, I'll just draw it and show. Suppose in the plot, if it is starting somewhere here and intersecting real axis, this particular thing what we are considering is as frequency. We are calculating frequency omega here, and that frequency is called phase crossover frequency, omega pc. This particular frequency which is actually intersecting real axis. Okay, so this frequency is called omega pc, phase crossover frequency. Sorry. So here what we will do is we'll consider omega is equal to phase crossover frequency, and I mentioned if it is intersecting the real axis, what we need to take is the imaginary part should be equated to 0. Okay, so from where we consider is I'll explain why we are taking this point. Okay, so omega equal to omega pc implies equate imaginary part to 0, and omega pc into 1 minus 0.05 omega pc square is equal to 0, and compute omega pc equal to root of 1 by 0.05, that will be equal to 4.472 radians per second. Okay, this will be phase crossover frequency. Okay, now what we need to do is we need to substitute this phase crossover frequency in the real axis. I mean in the real part. What is the real part here? Real part is nothing but this particular so in this expression real part is this one. This is real. Okay, just substitute omega pc. I mean this omega value is equal to 4.472 in this expression. What you get is at omega pc g of j omega into h of j omega is equal to 0.05 k divided by 0.6 omega square, that is equal to 0.05 k. What is the omega value? 0.6 into substitute omega is equal to 4.472 square. So if you compute this you will get minus 0.00417 k. Okay, so this is the magnitude. This is the magnitude where this plot will intersect the real axis. So if you compute this distance from the origin, that is nothing but 0.0417 k. We don't know the k value of k. Okay, I'll just mention it here. Okay, this is the particular, this distance is nothing but this point, this magnitude point is nothing but minus 0.00417 k. Okay, since this is the type 1 system and third order, here if you observe, it is actually minimum phase system, phase system, and there is no zero in the system. So in the transfer function we have all the three poles, and this is a type 1 system, and we are having the order of 3 since there are 3 poles. So we need to evaluate C1 now. Now we will be evaluating C1 to represent it in G of S and H of S or omega plane. Okay, so to evaluate the plot of C1 from this equation 3, right, this particular equation, what we will do is substitute omega equal to 0 here in this I will mention it as equation 3. Okay, this is equation 3, and substitute omega equal to 0 and omega equal to infinity to know the starting and ending points of the plot. This is only for C1. Okay, C1, if you observe, if you observe C1, it is actually starting here at omega equal to 0 plus, and it is going to omega equal to infinity. Okay, what is the angle here it is making? It is actually in terms of negative. I mean, if you are going clockwise direction, it will be minus 90, minus 180, minus 270. Right? It is tending towards minus 270. Substitute and sorry. So the magnitude and the phase to be calculated at omega equal to 0 and omega equal to infinity. Okay. To evaluate C1 from equation 3. Okay, magnitude is equal to G of S into H of S. We can take 0.05 k here, omega into root of a square plus b square, that is 1 plus 0.5 omega square into 1 plus 0.1 square. Okay, so from here, this is nothing but a magnitude, and we'll draw phase also. Phase will be, we have denominator as one pole, so it will be minus 90 for the pole at origin, and tan inverse of b by a, it is 0.5 omega minus tan inverse of 0.1 omega. Okay, this is the magnitude and the phase. Just check magnitude and phase from omega equal to 0 to infinity, are initial and final points. Okay, for omega equal to 0, if you substitute omega equal to 0 in the magnitude, so denominator is 0, that means in 0 if it is coming, magnitude will be infinity. Therefore magnitude is equal to infinity. And what is the phase? Phase will be, if you substitute omega equal to 0 here, tan inverse of 0 is 0, and tan inverse of 0 is 0, so left over is minus 90. So minus 90. Similarly, for omega equal to infinity, magnitude, substitute infinity in denominator, magnitude will be 0. Because denominator, if it is in the denominator part, if infinity is in the denominator part, magnitude will become 0. Similarly, for the phase, this will contribute, if it is infinity, tan inverse of infinity will be at minus 90. This is also at 90. So minus 90, minus 90 and minus 90, it will become minus 270 degrees. Okay. So now we'll represent for this particular plot a polar plot for this particular plot. Okay. So C1, right? We are considering only C1. C1 is from here to here at omega equal to 0 to omega equal to infinity. In j omega axis, this is j omega in S plane. This is S plane, and if you map this in G of S plane, G of S into H of S plane, how it will become? This I will take it as, since it is j omega, I will take it as JV. Okay, this is eta. This I will take it as U. Okay, so what is the, at omega equal to 0, you will be having minus 90. Minus 90 will be here. Minus 90, 0, minus 90, minus 180, minus 270. So here it will start at omega equal to 0, means at omega it will be here. It will start somewhere here, and ending point it will travel this way, and ending point is minus 270. Right? At omega equal to 0, magnitude will be 0. Here magnitude is infinity. Right? That's why I selected here. Magnitude will be 0 and it will terminate at origin, making an angle of minus 270. So this is G of S into H of S plane. So this is how we map the first one. This is C1. This is nothing but C1 mapping is done. So what is C2? Now C2 will be from infinity to minus infinity. So in yesterday's class we discussed some conditions. If you are having the plot on right half of S plane, and it is going from minus infinity to infinity, making the radius infinity, what are the conditions we discussed? The S term will tends to infinity r into e power j theta, right? So consider for C2, case 2. So here we will be writing for all the 4 cases, C1, C2, C3 and C4. C2 mapping of section 2. Mapping of section 2. Okay. So this can be done by selecting S equal to limit r tends to infinity r e power j theta. Why? Because as you see in the S plane, we will be starting at minus infinity and this part actually. At infinity, omega equal to infinity plus 2 omega equal to infinity minus. So this whole thing will be infinity actually. Our radius will be infinity. Therefore, for any point, if you want to select, if you select any point in between this right half of S plane, this condition will be satisfied. So the angle where it makes, what is the angle here? This is 90 degrees. So from here, if you consider from angle, this is 90 and this is minus 90. Therefore, this theta will vary. Theta will vary from 90 degrees to minus 90 degrees. Why? The direction will be clockwise. We are selecting C2 from here. It will travel towards this way and ends up at infinity. Omega equal to infinity minus. So the angles will be, starting angle will be 90 and ending angle will be minus 90. That's why theta will be varying from 90 to minus 90. So if a general expression is given in time constant form, we are having time constant form 1 by tau s plus 1, s tau plus 1. See, if you are selecting any value of uh, s here, s tends to s tends to infinity, radius tends to infinity. Here radius tends to infinity means this whole s term will be tending towards infinity in terms of a magnitude. Therefore, how can I write infinity plus infinity term time constant plus 1, right? In terms of a magnitude, this will be infinity. This is already infinity. Infinity plus 1 will be infinity indeed. Okay. So from here, 1 plus s tau will be equated, will be approximated to s tau. Okay, so from the equation 3, just see the equation 3. Here, whatever the time constant s tau, here s tau is there. I mean, once you convert into j omega, so here s into this s plus 1, it is tending towards infinity, and this is also tending towards infinity. So s into s will become s cube. Okay, just substitute that limit to this function, equation 3, that limit function to this equation 3. So, or I'll write it for equation 2 itself before converting into s into j omega. G of s into h of s. For simplicity, even if you do it for j omega, it's one and the same. So for simplicity, I am writing in terms of s itself. S into 1 plus 0.5 s into 1 plus 0.1 s. So this is the expression, and it will be approximated by applying this limit. This function, if you apply to this r tending to infinity, in which the magnitude r will be tending to infinity, infinity plus 1 will be infinity. Therefore 0.5k divided by s plus 0.5 s plus 0.1 s. Okay, this is how it will become. And if you take out this 0.1 and 0.5 outside, it will become 0.5 into 0.1, that is 0.05. Okay, actually this is not into, this is multiplication. It's multiplication, right? 0.5 s into 0.1 s. So 0.5 into 0.1 will be 0.05. That is k by s cube. Okay, apply this limit to that. Apply limit s tends to s. Apply this function to that. S equal to limit r tends to infinity r into e power j theta. So how it will become? K by limit r tends to infinity r into e power j theta whole cube. Okay, r tending to infinity, if you substitute infinity in the denominator, see this whole function r will be in the denominator. If any function having infinity in the denominator, how the function will become? Function will become actually 0. if it is going to the numerator. So this e power j theta cube, we can send it to numerator, it will become minus actually, isn't it? So 0 into r will be 0, r tending to 0, so substitute that e power j minus, minus means why minus, because it is going to numerator, 3 theta, because here the power functions, if you are having a power n power n, you can multiply that powers. So here for the function which is varying from 90 to minus 90, therefore theta should be substituted here, whatever the theta is there, and the expression will make, will consider this as 4. So this 4 theta will substitute for different theta, means for theta equal to 90 and minus 90. When theta is equal to 90, or we can take 90 as pi by 2 also, that implies g of s into h of s, that will be equal to 0 into e power minus j 3 pi by 2. 3 pi by 2 is nothing but minus 270, right? 3 pi by 2 means 270. So when theta is equal to minus 9 pi by 2, g of s into h of s will be 0 into e power minus into minus plus, so j 3 pi by 2. Okay, if you draw the contour for this one, the contour, if you draw the locus for this particular points, how the contour will become? So this is the function pi by 2 minus pi by 2 j omega s plane. So direction is towards this way, clockwise, and this is theta, and it is making a radius of infinity. This is infinity, r tends to infinity. If you do mapping for mapping in g of s, h of s axis, how it will become? I will consider this as jv, this as u, and see the plot is how it is starting actually. The plot is actually starting here at, it is of radius 0. Radius 0 means it's almost 0, it's negligible, but still it will make the circular shift from minus 3 pi by 2, minus 3 pi by 2, minus 3 pi by 2 means 270. Right, from here minus 2 pi by 2 means 0. See, this is 0, minus 90, minus 180, minus 270. So minus 270 it is actually starting, but actually radius will be 0. I am just to plot, just to show that I will be drawing beyond the 0. So it will start here, this point, and how it will travel? 0 to minus infinity, it is giving, it is making this particular till 0, from here to 0, and when omega is equal to, from 0, like it is varying from 3 pi by 2 to 3 pi by 2, minus 3 pi by 2 to 3 pi by 2, for pi by 2 to pi minus pi by 2 in S plane. So pi by 2 to 0, pi by 2 to 0 means halfway. Here 3 pi by 2 to 0, minus 3 pi by 2 means minus 270, halfway will be 0, till 0. From 0 to 270 again, 270 means till here, this will be on anti-clockwise direction, if you draw 0, this will be 90, this will be plus 180, this will be 270. So 3 pi by 2 means for this point, when you are going from here to here, it will be varying from here until it will goes here, and it will go from here to here. This is the direction. Okay, it will end up at 270. So this radius is actually 0. Just to show you the difference, I am just drawing. This is actually radius will be r will be 0. Okay, because r value here will be 0. This is negligible actually. Okay, so next thing is for C3. Here actually, if you observe C3, I'll write down mapping for C3. Mapping for section C3. Okay, in explain how the C3 is. C3 is from infinity to 0. It is actually reciprocal of the first case. It is just the inverse of the first case. So this particular point from here to here, omega equal to infinity to omega equal to infinity minus actually omega equal to 0 minus. So this is the C3 j omega and this is S plane. Okay, now what from the first case what we got, just observe the first case. For the first case, see, mapping is from 0 to infinity. We are getting this kind of plot. It starts from minus 90, ends up at 0, making the angle of minus 270. If this is actually a mirror image, right? If you are drawing for C3, C3 will be here. It is mirror image. So this will be also a mirror image. Okay, like manually you can check it for manually also, but anyway we know that this is a mirror image, so we can proceed this way. And if you want to solve manually, you can substitute same procedure, omega equal to 0 to infinity. For omega value, you have to calculate m, that is magnitude, and the p phase at omega equal to 0 and omega equal to infinity to compute this. Okay, just reciprocal. Okay, I'll just write directly this point. It is just as the same case. Okay, so it will be JV. It will start at this point and it will go this point and it will end up here. This will be omega equal to 0. This will be omega equal to infinity. It will actually starts at omega equal to infinity. It is reciprocal, right? So it will start at omega equal to infinity minus this way it will go. G of S, H of S, plane U. Okay, this point also, as we computed this point in the first case, at this point magnitude will be 0.00417 K. Okay, so this is how we can map section 3 and fourth point. Now mapping of section 4. Mapping of section C4. How the C4 actually looks in S plane. C4 is nothing but this point, right? From here, this radius will be 0. R is equal to 0. R tends to 0. And from here it is actually making an angle. This angle here it is making minus pi by 2. And here it is making pi by 2. Okay, it is going this way, anti-clockwise. This is C4. J omega. This is S plane. Okay, so now what we need to do is we need to map the section 4 using this S plane. by varying from minus pi by 2 to pi by 2. Say, right? Since here radius is 0, same function whatever we are considered for C2, radius will be tending to 0. So how it will become? S will become S is equal to limit r tends to 0, same function r into e power j theta. R tends to 0. There r tends to infinity because the radius is infinity. Here the radius is 0 in this case because it's just circulating the imaginary axis, origin, sorry, not imaginary axis, it is it's encircling, semi-encircling the origin. That's why the radius will be 0. Okay. So from the equation 2, the general equation g of s itself will substitute. In this case, if r tending to 0, so in how the time constant form will be converted? Say 1 by tau s plus 1 is there. Here, s is nothing but radius r tending to 0. If this is tending to 0, what is the leftover term? It is 1. So the whole thing will become only 1. Right? So just substitute there. G of s into h of s is equal to 0.05k divided by s into 0.5 s plus 1 into 0.1 s plus 1. So this will be 0, this will be 0, only s term will be left. So final expression will be 0.05 k divided by s. Okay, just apply the limit s tends to, sorry, r tends to, limit r tends to 0, r into e power j theta. Substitute this function in s. How it will become? 0.05 k divided by limit, if you apply limit r tends to 0, r into e power j theta. So r will be 0 and leftover will be e power j theta, and if denominator is 0, the numerator will become infinity. This is infinity e power minus j theta. Okay, so we'll just apply angles. Okay, so when theta is equal to minus pi by 2, because it is starting at minus pi by 2. S plane, if you remember, it starts at minus pi by 2. For that function g of s h of s, what we got is infinity e power plus pi by 2 and j pi by 2. Okay, when you are applying minus pi by 2 to this function, it will become minus of minus plus pi by 2. Similarly, when you apply theta is equal to pi by 2, g of s into h of s will be infinity e power minus j pi by 2. Okay, so here what does it mean? I'll just draw s plane and g of h of s plane for this function, where it starts at minus pi by 2 to pi by 2, C4, where r is 0 in s plane, j omega 5. If you are mapping, how it becomes? With the infinite radius, right? Infinite radius, it will start for this particular point when theta is equal to minus pi by 2. What you got is pi by 2 with the infinite radius. So it will start here. It will start here. JVU. Radius will be infinity, and it will tend towards this point and end up at minus pi by 2 with the radius of infinity. Radius tends to infinity. That's what the plot is. So the direction is clockwise. So this is how C1, C2, C3, C4 will be plotted, and what we need to do now is we need to combine all the points. So next step is combine all the cases, all the sections. C1, C2, C3 and C4. So for C1 what we got, I'll just C1 what we got, it starts at minus 90, it is going to this point and ending up at minus 270, right? I'll just stop it here. Just I'll continue the next plot. This is for C1. This is for the C1. C2, where it started at this point. Actually, let us consider this point as origin itself. Just to show the plot I am drawing. Otherwise, you can just put it to 0 and you can write C2 here itself. To show the difference, I am considering this point as origin point. Okay, and from here it encircled till here 270, and again it went to this point and it went till here, right? This is for C2, right? Yeah, C1, and this is C2, case C2. Okay, then from C2 what happened is it went on this point. This is nothing but C3. Okay, C3. Now from C3, what is the C4? What happened to C4? C4 is like this. Okay, it just encircled. This is the Nyquist plot. Okay, this is nothing but the direction is this way, C4. Okay, so now we need to write the stability conditions. Here this radius is actually 0. This radius I will mention r tends to 0, and this radius is infinity. R tends to infinity. Okay, and this particular point is minus 0.00417 K. So for the system to be stable, this is actually G of S, H of S plane. This is Nyquist plot. And see, in the previous class as I mentioned, if you are considering G of S and H of S plane, the encirclement, the point which we consider is critical point will be with respect to minus 1 plus J0. Minus 1 plus J0. So let us consider this point. If at all this point is minus 1 plus J0, this particular point, we can consider the system stability based on that point, right? If the point which we consider is in between minus 1 and J0 to origin, then the system is unstable actually. Okay, we'll write the stability conditions clearly. So from here, from the plot, stability analysis, consider this point minus 0.00417 K is equal to minus 1, because minus 1, why because we are considering the critical point as minus 1 plus J0. So since we are considering the real parts, what is the K we get here is 240. If you compute, k will be 240. So at this particular point, k will be 240. So if you consider k will be 240, and what happens if k is greater than or less than, conditions we'll see. Okay, if k is less than 240, if k is less than 240, just compute any value of k, less than 240. If you substitute any value of k less than 240, the shift, the point will be selected somewhere in between origin and this point, right? The point, the critical point, or the crossing point, this whatever it is crossing, right? Wherever the plot is crossing, in between the origin and -1 will be there. So if you consider this plot, how it is traveling through the Nyquist plot, so indicating the directions of it, it found that -1 plus j0 is not encircled, because where -1 is coming, -1 is coming at k equal to 240. If you are considering less than 240, there won't be these encirclements. K value will be somewhere here. Okay, -1 will be somewhere here. And if you are considering k value less than 240, the encirclements will be shifted this way towards the origin. Okay, therefore in this particular case, if you are seeing this -1 point, and the path, if the -1 point is on the left side of you, if you are traveling this way, if you see the -1 point on your left side, the system is stable. In a junk way, you can remember this way. If you are traveling in your Nyquist plot from the starting to ending, if you are enrouting from the starting to ending, if you see the -1 point or critical point on your left side, then the system is stable, as simple as that. Okay, then you need to check with the poles also. If any poles are lying on right half of S-plane, if any pole is there on right half of S-plane, system will be unstable. This will be applicable only if you have a poles on left half of S-plane. Okay, so for this condition, system will be stable. System is stable. Okay, so another case is if k value is greater than 240. If k value is greater than 240, this critical point will be shifted. Like this particular plot, it may go beyond -1, and then it will encircles that -1 actually. If it is on right side, see, if your plot is going this way and -1 is on your right side, then the system is unstable. Sorry. If you are -1 point, see, for any values of k, if you substitute greater than 240, say 400, if you are substituting, if you substitute 400, you may get around 1.5 or some value in between 1 and 2. That means this plot will be going beyond -1 point. -1 will be on right side then. That critical point you can observe on right side. If you are taking k value greater than 240. As I mentioned, that -1 or a critical point should be always on your left if you are traveling in the path. So for this condition, system will be unstable. System is unstable. Okay. So from this, what we can understand is the range. As the question, they asked, we need to find the range of k where the system is stable. So if you are selecting any k value in between 0 and 240, 240 will be here, right? 0 will be here and 240 will be till here. For this particular range of k, the system is stable. Beyond that, system will be unstable. Okay. Now the range of for the system to be guaranteed stable, the k will be selected as 0 less than k less than 240. So this is the range of k to be selected for this particular problem. Okay, so we'll see another problem with another type by selecting pole also or 0 also in the problem. If you have a 0 in the problem, how the system behaves, how the system stability varies, we'll see in the next class. Okay.